Okay, so hello everyone, welcome to the second lecture today. It will be given by Lau from Quarks Interactive. So Lau, thanks for accepting our invitation. It's good that we have you with us, and we are looking forward to your talk. And the Zoom is yours. So good luck.
Thank you, Pavel. Hi, everyone. My name is Lauren Cerniță, and I'm the CEO of a company called Quarks Interactive. We've been working on a game called Quantum Odyssey for the past 3.5 years now. What Quantum Odyssey intends to be is somewhere on the cross between an education platform for quantum computing and a video game. So there is so much to talk about it. I don't know if I can do justice in 1 hour. This is 3.5 years of work in which it wasn't just me working. So our team is now 5 people. And yeah, we are trying to do something really massive, take the idea of learning quantum computing, make it extremely fun, make it as fun as it can get. Yeah. And you'll see what I mean by that. You'll see how far we've managed to make progress, and that you can actually take something that looks really, well, some people could say it's awful, yeah, like linear algebra, and just gamify the heck out of it and make it that a 12-year-old can solve computational problems using quantum physics as if the person would just be playing Match 3 and 1 or Candy Crush, or I don't know, some sort of mobile video game. That's what we try to do, right? So there is one thing I want to mention before. Since you guys are running a hackathon and we are making here games using quantum physics, maybe we need to think about the idea of separating quantum games in 2 categories. This is something that's been on my mind for quite some time, because I would really like to be able to find quantum games and know that there are some quantum inspired games in 2 different categories, just like roguelikes and roguelites, yeah, something like that. For me, a quantum game would mean that we take a phenomena from quantum physics or some sorts of equations or some dynamics of quantum systems, and we create a game out of it. So the game itself and the rules of play are the mathematical rules behind the equations. Yeah, that would, for me, would mean a quantum game. For a quantum inspired game, I would give as an example quantum chess. Yeah, so the rules of play are based on the dynamic of an existing game or some game that, or some rules that have nothing to do with quantum physics. And in that game, or in that game mechanic or mechanics, we insert quantum physics phenomena. So for me, that would be a quantum inspired game. And that would be really awesome to see it at some point. And because then we would know, right, so how deep have we went into gamifying the mathematics behind quantum physics. And at the same time, we would know, right, what impact does quantum physics had on existing game mechanics, on an FPS, on a shooter? Yeah, could you teleport and be at the same time unteleported? Yeah, and could those kind of quantum physics phenomena have successfully been implemented in some games? And what are those games? So I would really love if we could think about that and be able to kind of separate and be able to distinguish between these 2 categories in the game industry. Right, so I'm going to show you mathematics because you guys love quantum physics, so that's why we're here. So let me show you how we managed to take the whole gate model framework, so stuff that you have on an IBM quantum computer today. So everything you could do on a quantum computer today from IBM, you could do in Quantum Odyssey. And not just that, but Quantum Odyssey itself is connected to IBM hardware. And this feature will be live in a matter of months now. And yeah, we'll talk about that later. So let's start by looking at quantum gates. So this is what you have on the, if I can move my window, on the right side here, this is a snapshot. It's a GIF from Quantum Odyssey. What Quantum Odyssey does, it looks at the Hilbert space which means if you think about a qubit as a vector on a block sphere, quantum odyssey doesn't do that. Quantum odyssey tried to get rid of that idea, because when you're computing on a quantum device, you need to think about the whole Hilbert space. So quantum odyssey is showing you the Hilbert space. So in this example here, we have a single qubit. This would be a block sphere with a vector pointing down towards the one state, because what the mathematics show here is that we have a state vector phi. That's a linear combination with an operator of being 0 and 1, and we swap. Yeah. So if our initial vector would be a 0 state, so A would be 1, B would be 0 in this case, our swap operator would simply swap, make A a 0 and B a 1. Or, well, in this case, I think you can see here, A goes to 1. Yes, this means the 0 becomes a 1. Yeah, and the power of visual, understanding this thing visually is really easy, because I mean, it's already hard to explain quantum physics, like talk about Schrödinger cat with someone and not make a mistake. But visually, it's impossible to make a mistake with this representation. So if our initial state vector would be a 1, it would be swapped to a 0. So our ball would go the other direction, right? So that's the behavior of an X gate. Y gate. This is the first peculiar gate that you have in quantum physics. Why? Because it's non-standard to classical computation, because you have phases here. So in case your qubit start state is 0, it will go and get a green phase, which is I. So if you look here in algebraic form, your Y gate is defined as this operator. Yeah, and in the bracket notation, or cat notation in this case, this is what you get. So if it's 0, it gets a green phase, it goes to 1. And if we have an X gate before, so let's consider our starting phi vector being a 1, then it would go back to 0, but it would get a gold phase, which is the number minus I. Yeah. For a Z gate, nothing happens if your qubit is 0. I think you guys can remember. And if you look at the operator, you will understand why it looks like an identity gate. But it's different from an identity gate because it's got a negative sign here. So in case the qubit would be a 1, you will get a red phase. I think this already kind of shows you that we use blue when there is no phase. So number has only a real part. We use red when the phase is negative. So when the real part is negative. And we use, for example, in this case here, green when the phase is an imaginary part and it's positive, and gold when the imaginary part and there is no blue, there is no real part, and only the imaginary part is negative. Right? All right, now we are talking about Schrödinger cat. So what does the Schrödinger cat do to my Hilbert space? And that's really hard to show even on a block sphere, right? So yeah, if you start from the 0 space, you get 2 equal amplitude, but smaller balls going to 0 and 1. So you can already see quantum dynamics visually. I mean, just trying to explain this doesn't make much sense because, yeah, it's hard to explain it using normal language unless we have to resort to mathematics. This is your operator. This is what the Schrödinger cat does. This is your Hadamard gate. And you can already see the difference. And you can already think about, wow, quantum computing. It turns out that, yeah, normally you would think about probability when you would think if the cat is alive and dead, but that's not true. In quantum computation, you can distinguish between if the cat was dead and then the Hadamard gate was applied, so we have the Schrödinger cat effect, looks quite different than if the cat was alive. Yeah, so it was a 1 before the Schrödinger cat gate got applied. We got blue, blue, and blue, red. So you see the phase remembers. So we are no longer talking about a probabilistic effect. We are talking about a changing phase of the amplitude of the qubit. And that's the beauty of visual. Yeah, try to explain this to someone without visuals. I'm not sure you can. Right, entanglement gate, CX gate. You have here the table of what the gate does. This is how it looks like in algebraic form. If you start from 0, nothing happens. The visual already can show you why, right? So if the leftmost qubit is 0, in these two cases, the line is just going down, right? But if the leftmost qubit is 1, no matter what the right qubit is, then we get this X gate happening. Yeah, so you can see that in this case, there was an X gate applied. So the 0,0 state becomes 1,0 state, and from 1,0 state, followed by a CX gate, the rightmost qubit gets flipped. So we get a 1-1 case. And again, the beauty of seeing the whole Hilbert space. So no matter our initial condition, if it's a 1-1, get to see that it would be a 0-1. Yeah, so you would understand all possible inputs, what they would translate, and what would be the all possible outputs. CZ gate, same thing. You can already understand something interesting here, right? So if the CZ gate, all it does is apply a phase in the case of both qubits being 1, right? Then there's this mysterious phenomenon that people keep struggling to learn, the idea of phase kickback, right? So the moment you use a CZ gate, it's not just that the slave qubit has a phase now, but also the phase is received, and well, I don't know what's the proper word here. I don't know if there is one. The both qubits, yeah. So both qubits get to have a phase. The moment you use the CZ gate, you literally swap the phase to red on both of your qubits. You can see this visually. I mean, in this case here on the right, the X gate was done on the wrong qubit, so that's why I don't get to see the ball changing color. Right, so if you want to see the ball changing color, this is the case when the leftmost qubit is a 1, yeah. But in this case, we have both qubits being a 1, and then you'll see that if only both qubits are 1, then the CZ gate gets a color. Why? Because again, a CZ gate does not act as a CX gate. If you look at the form it has, it looks like an identity operator with the exception of having a -1 on the last element, right? So this means although we flip the first qubit and then we follow with the CZ gate, the color, the phase would not be applied to both qubits because the second qubit is still 0. Therefore, it doesn't get a phase. All right, let's look at the Bell state. So if we start with 0,0, yeah, then we flip the leftmost qubit, we get a 1,0, so our ball goes to 1,0 here. I have this annotation bar, which I don't know if you guys can see it, but I hope you can. And then we apply a H gate, so a Hadamard gate. We get 0,0 and 1,0 with a phase, yeah, because the phase is applied in this 1,0 case because of the property of the Hadamard gate. Remember how it looks like. The operator is written here. And then we use the CX gate. We obtain a Bell state. A Bell state is interesting because you have 0,0 and 1,1. In this case, you have 1,1 with a phase, but it's relevant because when you measure, you don't get the information from the phase. And that's a problem of quantum computation. Measurement destroys phase information. So what's fun about the Bell state and what puzzles us since the beginning of time is the idea of, right, if I get a situation of 0,011 and I measure one of the qubits, regardless which one I measure, I immediately know the value of the other qubit. So given I would have a framework, reference point for transmitting the information, so the information won't travel faster than light, but the fact that the second qubit would be exactly in the same state as the first qubit I measured, it's fantastic. And no matter where this happens, no matter the distance between the qubits, we can use this idea to do quantum teleportation and really cool stuff. Yeah, so this inspires many people to study quantum physics for the idea of creating some communication channels. which would do some really impossible things, especially because it will be unhackable. Because if you lose the information of a qubit, you lose the information of the other qubits. So you know in real time if there is an eavesdropper in your quantum communication channel. Right, so what is this? What have you seen? So yeah, I showed you just some basic gates, right? So some basic Clifford gates, but there is no limit. So you could go well beyond the Clifford gate. You could use gates that are not unitary. Yeah, so the bipartite, you can use any type of gate. You can do any kind of linear algebra with this tool. So people are using it to study linear algebra. Yeah, so you can explore the properties of any matrix, and you could create any kind of computational challenge as a puzzle. And I will show you how to do that later. But the idea is any kind of physics phenomena, such as the Honge mantle, or I don't know, EV bond checker, or whatever you can think of, you could literally encode it. As long as it can be written in algebraic form, you can encode it in quantum odyssey and create a puzzle out of it. Yeah, and you can teach people visually what's happening behind the real physical apparatus where this experiment has been executed on. Phase kickback. This is the thing we were talking about. So the fact that the phase goes both ways. I don't know if it makes more sense to go deep into it. The idea is if you have a phase, the phase is retained. So a CX gate would do nothing in this case, but in this case, it would flip the phase. You see, so applying a CX gate would flip the phase and always on both qubits. So in the 1-1 state here, we'll definitely get the phase kicked to the first qubit. And if we resort to doing a H-H, so this is an X, the beginning, then we have a series of H gates, we have a control X, and then we have another series of H gates. You could see that the fact that in this first case, our qubit state went to 0, 1, and from here obtained 2 phases. The fact that these 2 phases were obtained kind of collapsed during quantum interference. So this explosion you see here is what scientists call quantum interference. When you have opposite phases and they collide, then it's as if that quantum state never existed in the first place. So if you can imagine 2 Schrodinger cats on top of each other, if you imagine the balls going through, even the Schrodinger cats are Hadamard gates, it would go through the first, we would have 2 balls, and then it would go through the second, we'll have 4 balls, but with opposing colors. So you'll have 2 collisions. One collision would amplify the amplitude, as is this case, and on the other 3 collisions would destroy the amplitude. So we would get a big ball from 4 small balls. And in this case, because of the phase, and as I said, the quantum computation keeps track of the phase. Nature keeps track of the phase. In this case, we get a completely different result just because of the phase, right? So the algorithm is perfectly symmetric with the exception of pushing it to go through a channel where there is a phase. So the ball gets a phase, and because of the phase, we get a completely different result at the end. And that's the power of phase kickback. Right, now, with quantum odyssey, you can do really crazy stuff. So crazy stuff would be searching a database, which you have, I don't know, let's say in this case, yeah, we have 3 qubits, so you have 8 possibilities in our database. And we would mark some states. Let's say we are looking for 2 aces in a deck of 8 cards. Yeah, so we have, as you can see here, let's say we have 8 cards. We have 8 blue balls. After that, we mark 2 of the cards. So again, we are showing you here the power of phase in quantum dynamics. So this is called an oracle function. An oracle because, well, it's a bit fake. Yeah, I mean, the Grover search, if you know what you're looking for and where it is already, then there is no really real point to actually calculate what it is. But there is something interesting from Grover, and I will tell you about it later. But as an idea, yeah, you build an oracle, you mark 2 of the balls red, meaning 2 of the balls will have opposing phases for all the balls. Right now, if you were to measure your quantum circuit, if you were to run this on a quantum device, from measurement theory, we lose phase information, right? So you would get a perfectly equal distribution. If you measure 1,000,000 times, you'll get 1/8 each of these cases multiplied by, I don't know, random chance and the errors in the circuit and the errors of the gates and whatever other hardware problems we have today. But you will not get anything interesting, right? So it's literally as if, although we know the information, we know which gates are, or we know which states are the ones that are the ones we want to obtain, we won't obtain them. So this information is only available if we are, I don't know, Ant-Man from Marvel. Yeah, otherwise we would not know what's going on in the system. But then we start building the diffusion operator. And I'm not gonna go into the details. It looks pretty complicated, but that's what it does. And the power of visual, you can already see and you can already distinguish that something magical is happening here. So we have a first interference, we have only 4 states, and then we get this results. So all these empty slots mean there is no ball going towards them. So literally we managed to create a full circuit, which in mathematical form looks like this, in a visual form. And as a result, we managed to see with our own eyes, not read the mathematics, that we get just 2 results. And now if you compile this in Qiskit, and Quantum Odyssey will allow you to compile it in Qiskit and run it on quantum hardware from whatever vendor you prefer, then you would get this result. If you run it 1,000,000 times, you get 500,000 times 101, 500,000 times 110. Right, so yeah, like I said, so with Quantum Odyssey, you can export to Qiskit because this visual method is, you can think of it as a complete no-code method to quantum computation. So we have people who are gamers, people who know nothing about linear algebra or nothing about quantum computation or quantum physics whatsoever, who managed to finish all the learning modules in Quantum Odyssey. And for those people in particular, we are now building online challenges and let them create interesting challenges to share with their fellow players and see how many quantum optimization problems, how many quantum algorithms we can build, we can optimize, we can enhance in some way or discover something new. Just understanding the visual method and how the visuals play in between themselves. Yeah, so if something goes through a red channel, then goes through a green channel, will become a gold ball. Yeah, so there are some rules, and these rules are exactly what mathematics give us. Yeah, but instead of doing mathematics, you understand it as just a visual toy that you play with, and you can encode any sorts of problems up to 5 qubits in Quantum Odyssey, and you could have a gamer solve the problem for you and optimize your circuit. Yeah, so you can extract and at the same time import any Qiskit, any Quast circuit in Quantum Odyssey, press a button and it gets compiled, it becomes a visual puzzle. You can save it and you can publish it, and you can design a bare state vector as an output, like ask for, right, so this is how my gates are placed. I would like this particular state vector, which I would like to obtain, and that's the puzzle. Yeah, so then it comes for the gamer to find out using whatever gates you allow the gamer to use. He or she can try to optimize and solve, and first try to get your state vector from the compilation problem you created, and second, compete on a score base. If another gamer can do even better, can use less gates or can use less complicated gates than the previous one did. Yeah, so that's the idea behind Quantum Odyssey. We're trying to create a huge community of people who just play with quantum computing, right? So instead of having to do, I know, 20 years of research and learning, you could just hop in. Some scientist or some other gamer would create some challenge And yeah, if you know the rules, then please download Quantum Odyssey. Well, if you want to learn how to do quantum computation, just download Quantum Odyssey, play with it, and solve as many puzzles as you can. There are over 10 learning modules. So there are over, I think, like 20 to 30 hours of just learning, of just sitting down and learning with a huge encyclopedia and all kinds of information that describes quite in detail stuff about even error and how to correct circuits, how to optimize the circuit, how the process of thinking about quantum computation goes. So it really teaches you the whole foundation for understanding how to use one of these devices. Yeah, and I'm giving here IBM because yeah, we are connecting the game to IBM hardware, which means that what we are doing is literally coding on an actual quantum computer. Yeah, and you can get your after measurement results from a real hardware if you prefer to do so. If not, then I mean, just the idea of creating the quantum circuit up to phase that keeps the phase information, that's more than sufficient to really advance the field of quantum computation and really kind of push the barrier of, right, we understand there are new algorithms. We discovered something new and exciting that you could do with the quantum computer. And here is the circuit. So if you guys can help me get a game and solve all the challenges and think of new challenges, then I think this is something step forward for science. And we can have a big zoo of solved quantum compilation problems from people all over the globe that are constantly being optimized. So as I said, there's always the idea of if somebody else can solve the problem which was already solved by someone, but in a more optimal way, meaning less gates or simpler gates. Yeah, and this is the QR code that you can just go and get. Right, I see there are some chats. Okay, it's not a big deal. Then let me just hop into Unity because I think most of you play with Unity, and I'm gonna show you what are the new features of Quantum Odyssey. We still have some time. Pavel, should we leave time for questions, or how long should I play with the game?
Yeah, so how much time do you need? Because I think that as for now you can take your time, because so initially we scheduled this lecture for 1 hour, so until 3 p.m. Polish time, but in fact we are not in rush, because later there will be a break, so the next lecture will be at 5 p.m. so no worries, we can extend the lecture, so just take your time.
Okay. Okay, let's do it interactive then. I'll open the editor, I'll show some basic stuff, and then if there are any questions or you want me to show something in particular, I can. Let me first adjust the audio. Yeah, I'm gonna put everything too low. So I jumped right into the editor, but as I said, the game comes with quite a lot of learning modules, which we will continue building on. So we have a strong team working on it. Right now, the game has 3 big chapters. The first one teaches you fundamental quantum computation rules using visual methods. So you don't learn mathematics. You learn how these rules play with each other. You learn how phase kickback is useful, why superpositions collapse things the way they do, why a CZ or CX does what it does, how to calculate eigenvalues without actually calculating eigenvalues, but understanding the graphical dynamic of when you have when you're doing a basis transform of some qubits. So stuff like that you can learn in the first chapter, right? So you start from bit flips. You start by learning how to flip a bit. Then you start by learning how to flip a bit with phase, with global phase, and how the phases play between themselves. This is really fun. Although you don't know anything about linear algebra or physics, you can learn complex numbers by playing this. Yeah. And then we go deeper into, this is the first module that teaches you quantum computation in the sense of, right, superposition, Bell states, how that translates into something more complicated, like elements of reality, the idea of GAZ, W states, why these states are useful, how to create them, what's strange about states that we tend to use in communication, in quantum communication today. And then you learn about the idea of not exactly teleportation, but swapping qubits. How you can swap the information from one qubit to another. So I don't know if you guys know about the no cloning theorem. You can't really copy a qubit, but you can swap it with another qubit. So if I have two qubits, one has some information, the other one has some other information, these two qubits would just swap information between themselves. And that's really fun and it's really interesting, the stuff you can do with swap operators. This really lets you explore the variety of possibilities and things you could do with swap operators. And this is about basis transforms. So this teach you the idea of why we chose 3 bases when we measure a qubit. I'm not going to go into detail because this one is a bit complicated, but yeah, and it's quite challenging. So it gets to be quite challenging, but again, like I said, we are trying to gamify it. We're trying to ease the learning curve, make it more accessible. And then chapter 2 and 3, hardcore teaches you about Grover search, and then on real world problems, which gives you a PhD challenge. So if you finish the second module, you learn the idea of encoding a problem on a quantum computer and the caveats and how to think about it. And it gives you then a challenge that asks you to go into the editor of the game and actually try to solve it. And I know some people tried, but it's really difficult. I said it's a PhD level challenge. So yeah, if somebody manages to solve that, please contact me immediately. We'll write a paper together. Okay, so this is the editor. And here in the editor, what I looked at is how to give you so much functionality that you could design absolutely any type of quantum computation problem. So you could design something on, I don't know, 5 qubits if you'd want to go that far. But yeah, I would say let's start with 3 qubits if we are learning how to create quantum circuits, or 2 qubits. And yeah, we also now or soon will give you the possibility to create challenges of many puzzles. Yeah. Which means literally you design a puzzle, then you design a second, a third, a fourth, a fifth challenge. You give them a description, you set some settings of what kind of gates are allowed. You can create more gates and you can enable them or disable them. I'll show you how that's done later. And you can create a full seminar that you could use in a class. You could give it as a homework to your students, in a sense. Yeah, you could just set a time limit. Yeah, so there's a time challenge. You can set a time limit. You can create some set of 15 puzzles, which are literally 15 computation problems, and you could see if the students are able to solve them, given what they learned so far. And if some students prefer the mathematical form, well, of course, you have it here. So you can see all the math behind the gates, which are used. So yeah, these are easy to copy out, copy in, and so on. So literally, we are trying to think of creating Quantum Odyssey, first and foremost, something that the teacher can use in the classroom, just be able to create homeworks for students with it, and also explain core concepts with it, and maybe, yeah, go beyond it, maybe ask them to design algorithms using it. So this is going to be quite complex, the idea of creating a challenge. We'll see how much we can continue developing it, in which direction we'll go. Again, the community is important for us. So like I said, this game is being developed for the last 3.5 years, at least. And I think it's going to continue to be developed for at least 3.5 years more. There's so much we want to do with it. We want it to be the full Bible of quantum computation. So have all the information you'd ever need to solve for an algorithm, to make it more optimized, or to create a new algorithm, discover a new algorithm. So that's what the editor allows you to do, to mess with existing quantum gates or create a new quantum gate. Now let me show you something. Let's do a 2 qubit. Let's do a H, Y, and an X, Z here. Right, so it immediately computes for us what the result will be, 0, 1, and 1, 1. With here we have an I, and here we have a minus I. Yeah, 0.73 something coefficient. You can calculate these things in your head just by looking at the size of the balls. And if I check, look, this is what I said, 0.70 and minus 0.70. So that's the power of visual, that you can already familiarize yourself with the colors, with the sizes, with stuff, which are the outcome of using certain gates, and you no longer need to think mathematically. You can just think in your head visually about circuits. And let me show you some of the options we have. Let's take this whole sequence we have here and save it as a gate. Let's test it. Let's say green gold. So I can save it, and I have it here, green gold. You see? Now I applied the gate, which looks like this. Maybe it would be useful if I would apply it with a little space between. Yeah. So that's the power of visual again. If we have this state, green gold, on 0, 1, 1, 1, and this gate that I placed here does exactly the same thing as this other gate, what do we know about quantum computation? It is reversible, right? So if you apply a gate and then you apply the same gate, or in this case, you apply a bunch of gates, and then you apply the same bunch of gates compiled in a single gate, which looks, I think it looks a bit crazy. Yeah, it looks like this. This particular gate here looks like this. You would get back the starting state. So in our case, we would get back 0, 0. And you can see quantum interference playing out. Red, blue, cancel, blue, blue, amplifying. And I think just by looking at it, you can see the rules of the colors, which are equal to the rules of complex number multiplication. Yeah, multiplying something with a real number, that's 1, as it's in this empty case, you see nothing happens to our ball. But here we have 2 paths, same as here. One of the paths is gold. So guess what? This green ball will become blue because green and gold extinguish and they take the blue neutral ice color. Yeah. The rules are really simple, guys. So the rules are something that we tested with 12-year-olds with a grant in UK, and all the kids managed to remember the rules after. So 12-year-olds can easily remember the rules and can easily do quantum compilation problems or decomposition problems using quantum odyssey. Other ways we can play with it is, and now things get a bit more complex. Yeah, we can create a custom gate of any size. Well, so far 1, 2, and 3, we're still testing out the feature. And we can, yeah, do, I don't know, do stuff like this. And we can preview the matrix. Yeah, sin of pi divided by 2 is 1. So, yeah, I didn't really change the matrix here. And this creates another gate for us, which we can place, and oh, it crashed the whole circuit because it's a 3-qubit gate and I placed on a 3-qubit gate on an unexperimented build. Excellent. Let's go back then. So the idea is that this feature gives you the ability to just copy paste and design any sort of gate that you have. For example, somebody gives you a homework. That's cool. And I know people who did it. I was one of them. So you can use this tool to solve homework. And if you study quantum computation, you can copy paste here the gate you have, save it. And after you do that, you place it, and then you can find the Clifford set or whatever operators you're asked in the homework to use or can't use or whatever, and try to decompile it and find, for example, the set of operators that were used to create this custom gate, the gate from your homework. So that's extremely easy to do when you have visuals in front of you, because like I said, so let's say we have a case like this. Look how many ways we could actually play with. Right, okay, let me explain a bit. So let's say we have some weird gate. I'm not looking at it, and I'm not gonna use these gates. I'm gonna use some completely arbitrary gates to solve this problem here. So I have some situation like this, 0, 1, 1, 1. That's what my professor gave me as my homework. I want this to go back to 0, 0 and be blue. How to go about doing it? Well, first thing, I would look at the colors. I get a green, so I would use something that would extinguish the colors. So green, and I remember about phase kickback gets extinguished, and I get red. Interesting. So if I have red, I wouldn't care. I would just place a H somewhere. I would prefer to place it here, you see, because if I would place it here, I would get many. I would get it split in many positions. And I remember that a H applied on the rightmost qubit. And again, that's the power of visual learning. But in this case, yeah, it would collapse, right? And I would get a single red ball going to 0, 1. So if a single red ball is going to 0, 1, this means my rightmost qubit has the phase, and I want to extinguish this phase. How to do it? Well, I could just put a Z gate in the next available slot or on the same slot, and now I have a blue ball. And now I have 0, 1. How to get to 0, 0 to 0, 1? Well, that's really easy. Just place an X gate. It's bound. We have 0, 0, right? So how easy and how fun can doing your homework become? Yeah, and that's what I'm militating for. Let's think about quantum games. Let's think about any kind of weird quantum physics or mathematics stuff that's really hard to understand. Wrap your hand around it or find ways to reason about those equations, and let's see if we can gamify them. Yeah, so what I'm asking is, let's create proper quantum games in which we are gamifying some equations, we're making them more accessible with less knowledge needed in order to solve those equations or those problems, or yeah, use those equations to solve some other problems. So let's start really heavily thinking about quantum games. That's my ask from you guys. And there are many other things. Of course, you can use angles, you can use theta, phi, and lambda. If you know about the Bloch sphere, I think these are familiar for you. You can put here whatever radians you want, and you can create a gate like that. And I don't know if you guys have any other ideas about ways you would like to be able to create gates. Just drop me an email, a chat on Discord. Yeah, I'm always on Discord. My website is this, yeah, quarksinteractive.com. Here is where you can find all sorts of information, including some movies. Our YouTube channel, I think, has like 10 movies. By now, we are trying to slowly start teaching quantum physics by visual methods using the channel. I know we have been a bit inactive lately because we are busy coding, but maybe in December or so, we'll again start thinking about, right, let's do cool stuff with Quantum Odyssey and yeah, promote the idea of learning quantum to reach a bigger audience. And like I said, you really don't need any background. If you just love games, then I think this is the perfect place to start learning quantum. Just play with Quantum Odyssey and yeah, just learn quantum because many really cool problems we know can be resolved by applying quantum computing. And yeah, that's the main reason why we have built Quantum Odyssey. So in my head, I'm thinking, right, if I'm a chemist, I know some basics and stuff, but I don't want to really bother with doing so much math and rethinking about ways in by studying CAT, for starting to learn CAT in order to be able to express what I would like to design using quantum computing and put on a quantum computer. And then second, I need to understand all these phenomena, and by how do I go about visualizing quantum superposition, and how can I create quantum interference here? I know it's possible, I don't know how. Well, all those questions can be answered by just playing with Quantum Odyssey. So if you have some background in which you know quantum computing could accelerate progress or could be applied to, the dream I have is that I can create a software, and this software called Quantum Odyssey would be more than sufficient for you to just spend a couple of hours with. And I'm really not asking for much, maybe that's an exaggeration, just half an hour, familiarize with the rules. You'll understand the basic elements in quantum computing and how it's different from classical computing. And maybe that would be sufficient for you to be able to express the problem. And yeah, make some progress, apply quantum to chemistry or I don't know, drug discovery, or finance, or whatever field you're studying. Okay, so Pavel, I think I covered most of the stuff I wanted to talk about it. Do you have some questions, or should we play with some ideas, or I don't know? What do you think?
Okay, so let's maybe first ask our attendees, and so are there any more questions to Laura? Because we have still some time, so I don't see more questions on our chat at the moment. So I don't know if you have some maybe other examples, you can show it, but anyway, we can also just finish a bit earlier. So no worries.
Okay, I'll show you some cool stuff. For example, let's do a GAZ state. So for the GAZ state, we have 3 qubits. Let's do it the other way. Maybe it looks better. So let's say we have the 3rd qubit, in our case, be both 1 and 0 at the same time. Yeah, the power of the editor, the editor allows you to see the result, the calculation of whatever gates you place here in real time. In solve mode or in challenge mode, when you're actually trying to solve a computational problem, here you would have expressed the desired solution. Yeah, and ideally you would pause the computation at some point and analyze what would be missing to obtain this result here. Yeah, so that's how the editor is different than solving puzzles. So let's say we want to design a state in which we will have, if I would measure any of the 3 qubits, all the other qubits, I would know what state they're in. And that's called the GAZ state. So this is a Bell state on 3 qubits. Basically, I would want to achieve something like 0, 0, 0 and 1, 1, 1 in my Hilbert space. How to go about constructing that? Well, if I know about Hadamard and just control gates and X gates, that should be sufficient. So all I would have to do is first break the balls in 2, because I want a perfectly equal amplitude state between 0, 0, 0 and 1, 1, 1. So the first thing, obviously, I will need to place a Hadamard to break my amplitudes. And now the question comes, right, how do I take this ball from 0, 0, 1, which is on an unwanted space? So I don't want to obtain this. I want this ball to go all the way here in the 1, 1, 1 slot. Well, how can I go about doing that, right? So I would need to clearly use control gates because they break my computational symmetry. What do I mean by that? It means that nothing happens if my 3rd qubit is 0. So this means this ball here will never move, yeah? But what I'll move is the ball from here. So I just jumped 2 slots. See in my LSB Hilbert space, now I have 0, 0, 0 and 0, 1, because I applied this X gate with a conditional on the 3rd qubit for being 1. So only if this qubit is 1, then it will force the 2nd qubit to be 1. So now I have 0, 0, 0, 0, 1, 1. And now I want to do the same thing, but again, just for this qubit, right? So I'm not happy with having just this qubit 1, because then this other qubit is 0. So I want to do now is again use it as the control and force the last qubit to be 1. And look at that. We've just designed a GAZ state using nothing but visual, just thinking about the visual. Yeah, now we have 0, 0, 0 and 1, 1, 1. So we just use the editor to design an algorithm that can achieve a state I'm looking for without actually doing the maths or thinking about it too hard, just looking at where the balls are falling and just designing a path for just one of the ball to go to somewhere else. Yeah. And maybe with this note, I can finish my speech, Pavel. And yeah, if there are any other questions or something, let me know.
All right. I don't see more questions on our chat, so I think that I will stop recording now.